In this section, we talk about the condensation of the Gobo Kimmage matrix. Let us explain what we want to do. Okay. See, we have a matrix relation here. This P is P1, P2. This vector is written like this. This vector is written like this, and this matrix written like this. What are they? See, Q1, Q2, Q3 to Q18, right? So this vector represents the nodal displacement of all the nodal points, right? Q1, Q2, Q3, Q4, Q17, Q18. Okay, put it here, and here is the nodal forces for the whole beam. Okay. P1, P2, P1, P2, P3, P4, P3, P4, and P18, right? So all these nodal displacement and nodal forces will be connected to each other, right? Because it is a solid beam. So the displacement in one nodal point will be related to the forces in other material points, right? They are correlated. The correlation is represented by this big matrix. Okay, so this is a 18 times 18, 18 cos 18 matrix, right? So it is a big matrix. Now we want to do the condensation. Condense. Okay, condensation. What you mean? The meaning is this. See, we want to find out the nodal displacement. We want to find out the deformation, right? So we want to find out the nodal displacement of each node, right? So the unknown is here. The condition is given here because this is the external force, right? This is the external force given. So we want to find out here. We want to find out unknown here, but Q1 and Q2 are not unknowns because Q1 and Q2 here is equal 0, are equal 0 due to the boundary condition here, the support, okay, fixed support here. We also consider the support here is fixed, okay, change it from roller to fixed. So the displacement here are also 0. So Q1, Q2, Q3, Q4, Q5, Q6 are equal 0. So these four nodal displacements are not unknown. Okay, the rest of the displacement are unknown. Okay, these are known and these are known. So we want to take these four quantities out of this vector equation because they are, we don't need to calculate them because they are already known. So we want to cancel this, cancel this, cancel this. How? What to do? We just pull this matrix out. For example, in the computer storage, you just delete this row of data, and also we delete this row, and here Q5 is low. We delete this row and delete this row, and also correspondingly we delete this column. The first row is deleted. The first column should be deleted too. The second displacement, nodal displacement is known, so the second row is deleted, so the second column is deleted. Okay, Q5 is known equal to 0, so this should be deleted and this should be deleted. Okay, after such kind of deletion, okay, elimination, this big matrix will become 14 by 14. Okay, originally it is 18 by 18, right? But now it becomes smaller, become a 14 by 14 matrix. Okay, we put this part to here, and this part to here, and this part to here, and this part to here, to form a smaller matrix. Okay. Okay, so we want to solve this condensed problem. Okay. Now these are unknown. Q3, Q4, Q3, Q4, Q7, Q8 are unknowns. Okay. How about this vector? These vectors are given. See, P16, what is P16 here? Why it is equal to minus 120? Because at this degree of freedom, the nodal force is minus 120, okay? The other nodal forces equal 0. Why? Because nodal forces are lost stresses. So nodal forces are the resultant forces. So this is in equilibrium. So every material point are in equilibrium. So the nodal forces in this point and this point are all equal 0 except this one. Okay. So in this way, this force vector is given. So and this stiffness matrix is given. So we only need to do the inversion to move this matrix here to calculate the displacement vector. Okay. This is the thing we want to do. We repeat it once again. We repeat it once again. We call it as QC, this as PC, and this is KC. So we get this, this, and this. And then we find out the inverse matrix and then multiply by the force vector, get the displacement vector. Okay, so in this way, all the nodal displacement can be obtained. Okay, means that all the displacement on the nodes of the elements are known now. Okay, so basically the problem has been solved. Now, one more thing, if you want to find out the reaction forces here, what to do? We can use the formula here. What are these formula? Okay, P1, P2, P5, P6. P1, P2, P5, P6. What are these formula? Okay, these formulas are this. P1 equal to K11 times Q1, but Q1 equals 0, so it doesn't count. No? K12, P1 equal to K11 plus Q1 times Q1 plus K12 times Q2, but all 0. Plus K13 times Q3, this one. Plus K14 times Q4, this one. Understand? So from this row and this column, we get P1. Okay, the multiplication of this row with this column will give you P1. Okay, written right here. Okay, in the same way, this row and this column will give you P2, written right here. Okay, these are the formula we need to have to calculate P1, P2, P5, P6. So basically, after all these calculations, the reaction forces are known, and all the nodal displacement are known, and then we can use this nodal displacement to find out the continuous displacement field by the shape function concept. Okay, we multiply the shape function with the nodal displacement to give you the continuous displacement distribution. Once you get the continuous displacement distribution, you can have the strain and the stress. Okay, now we want to talk about the final topic. Okay, we want to find out the stiffness of a typical element. Okay, we had already known that we have this formula before. Okay, this formula looks a little bit terrible. Okay, like this. But I just want to tell you, a lot of terms in this formula are equal 0. Why? Because the stress strain relation is simple. So sigma 11 related to C11 only. So right here, so only C1111, okay, epsilon 11 only. Sigma 11 related to epsilon 11 and epsilon 22, epsilon 11 and epsilon 22. So only C1111 and C1122 are not equal 0. Okay, so you have those shear component. So C1112 and C1121 equal 0 because we don't have epsilon 12 here. We don't have epsilon 21 here. So these two material constants are equal 0. So in this way, we can determine all the non-zero material constant and the zero material constant Okay, so once we do this, we find out that we have only 6 non-zero terms. 1, 2, 3, 4, 5, 6, right? So here, we don't have 16 terms. We have only 6 non-zero terms, okay? Because 10 terms out of these 16 terms are zero. So we write it like this one equal to this one, put it here, this one put it here, this one put it here, this one put it here, and this one put it here, and this one put it here. So we have only 6 terms. And also, we can compute this shape function for the string easily, okay? We use the one example, K2Q5, means that we put A equal to 2, B equal to 5, okay? K25 means that we want to relate it, the nodal force P2 to the nodal displacement Q5, okay, by this steepness component. Okay, we have the shape function before, and then from this shape function we can calculate the shape function for the string. Okay, and we find out that some of the shape functions are 0. So actually, in this formula, this 0, this 0, this 0. So we have only 3 non-zero terms, 1, 2, 3. And then we put this shape function into here to carry out the calculations, okay, one by one, and then you finally end up with K25 equal to this simple formula. Okay, so it is an easy calculation you can follow by yourself.